Today we're going to explore two fundamental concepts in calculus and optimization: concave and convex functions. By the end of this video, you will be able to define concave and convex functions, understand their geometric interpretations, and identify them using the second derivative test. These ideas are crucial for understanding the shape of a function's graph and for finding maximum and minimum values, which is a core part of optimization. Let's start with the idea of concavity. You might have heard the terms concave up and concave down. A function is concave up on an interval if its graph lies above all of its tangent lines on that interval. Think of it as a cup that can hold water. Visually, if we draw a tangent line at any point on a concave up curve, the entire curve will be above that line. It's like a smile. Conversely, a function is concave down on an interval if its graph lies below all of its tangent lines on that interval. This is like an upside-down cup, or a frown. Here, if we draw a tangent line, the entire curve will be below it. The curve is bending downwards. So concave up means the curve is bending upwards, and concave down means it's bending downwards. This geometric interpretation is key. Now, how can we determine concavity without drawing the graph? We use the second derivative. The second derivative, denoted f double prime of x, tells us about the rate of change of the first derivative, which is the slope of the tangent line. If the second derivative is positive on an interval, the function is concave up on that interval. This means the slope of the tangent line is increasing. If the second derivative is negative on an interval, the function is concave down on that interval. This means the slope of the tangent line is decreasing. Let's see this in action with an example. Consider the function f of x equals x cubed minus 3x squared plus 1. First we find the first derivative, f prime of x, which is 3x squared, minus 6x. Next we find the second derivative, f double prime of x, which is 6x minus 6. Now we need to find where the second derivative is positive or negative. We start by finding where it's 0. Setting 6x minus 6 equal to 0 gives us x equals 1. This point is called a possible inflection point. We'll use this point to divide the number line into two intervals, from negative infinity to 1, and from 1 to positive infinity. Let's test a point in the first interval, say x equals 0. F double prime of 0 is negative 6, which is less than 0. So the function is concave down on this interval. Now let's test a point in the second interval, say x equals 2. F double prime of 2 is 6, which is greater than 0. So the function is concave up on this interval. Since the concavity changes at x equals 1, this point is an inflection point. It's where the graph switches from frowning to smiling. Now let's shift our focus to convex functions. The definition of a convex function is closely related to the definition of a concave function. A function is convex on an interval if its graph lies below all of its tangent lines on that interval. This is the exact opposite of concave up. So a convex function is the same as a function that is concave up. The terms are often used interchangeably, especially in fields like optimization and economics. Similarly, a function is concave if its graph lies above all of its tangent lines. This is the same as a function that is concave down. So a concave function is the same as a function that is concave down. It's important to be aware of this terminology difference. In this video, we will use the terms concave up and concave down to avoid confusion, but remember that convex means concave up and concave means concave down. Let's recap what we've learned today. We defined concave up as a graph that holds water and concave down as a graph that spills water. We saw that a function is concave up when its second derivative is positive and concave down when its second derivative is negative. We also learned that a point where the concavity changes is called an inflection point. Understanding concavity is a powerful tool for analyzing the shape of a function and is a fundamental concept in calculus and optimization. Thank you for watching.